And that way, what I say will have to be more carefully said. Okay, if I say everybody leaves this room and and it doesn't happen, it means what? That somebody didn't leave the room, not that everybody didn't leave the room, not that everybody stayed. In other words, the opposite in math of everybody does something is not everybody doesn't do it. Even though in English, if you put not in a sentence, if I just say, I am crazy, and I want a negation of that, that would be, I am not crazy. But there's no real quantification there, okay? But if I say all people are crazy, you do not negate it by saying all people are not crazy. You don't simply put the not in the middle, because when you have a quantified statement and you negate it, you're negating the quantification as well. And so if I say not everybody does something, that means somebody doesn't do it, okay? So you have leave the room, everybody leaves the room, nobody leaves the room, somebody leaves the room, or somebody doesn't leave the room. There's 4 different statements there, and everybody does, everybody doesn't, or somebody does, somebody doesn't, are not negations, okay? And people mess that up. And as far as if we had a logic test, I might test you on such a thing, and that's not a hard thing to be tested over, but if you haven't thought about it, you'll probably get it wrong. Okay, so now, as far as truth tables go, I'm not going to, as far as tests, I'm not going to tell you all about tests right now because we're not ready to take a test. But as far as the truth table goes, I'm not going to make you to make a lot of big truth tables. Don't worry about that. On the other hand, I want you to know how to make a truth table. Okay, so I might give you a sentence on a test that has a fairly complicated statement and tell you what the parts are. This part's true, that part's false, and so forth. So in the end, is it a true statement or a false statement? So you'll need to know if I have an T and an F and an and statement that that's false. Or if I have an if-then statement with a false if and a true then, that that's a true statement. You might have to know that, okay, to do it. So I want you to have the knowledge, but I'm not going to put you to a lot of trouble to fill out these things. A big truth table takes forever and easy to make mistakes, but you can understand it without having to prove it, okay? Now, what I'd like to do today, unless you have some questions about the logic, and you can have questions whenever you can get around to reading it if you haven't studied it yet, whenever you do, we can answer questions about it because we're going to be using the logic all the time. And I'll be showing you some things maybe today if we get to it of where we use the logic. Now, I'd like to do a trig review first or next or something and see where you are on that, because now what you guys have been doing is reading about functions. When we get to functions, which is going to be after the trig review and after some sets, so it's going to be a couple days before I talk about functions, but I'm not going to define functions like the book does. The book describes functions in section 1. It doesn't define mathematically instructions. It tells you about it, and it's like a dictionary. The author with the definitions should be very precise mathematically, but sometimes we describe stuff because it's really hard to define it mathematically. Now, a lot of times in calculus, you don't prove everything, and so we don't have to have everything defined because you're trying to learn about it as well as do it, okay? And so I'm going to make definitions because I'm going to do the course a little deeper because it's an honors course. I do it deeper anyway, but I say it's like an honors course. Somebody say, oh, it's an honors course. Well, now it's okay. Anyway, we're going to talk a little bit more about stuff than the book does. And so I've got to be a little more careful about how I say things than the book does. So the book says a function is a rule. My first question is, what's a rule? And the book doesn't define what a rule is. Well, that's what a dictionary does. If you think about it, dictionaries don't define things. What they do is they give you other words that are like the word you're trying to understand. And if you will look up each of the words that the dictionary uses to explain some words, you're going to find out when you look at the next word, it will have the word you just looked at as an example of what it means. And so a dictionary is what's called circular. And circular reasoning is not logic. If you do things with circular reasoning, you can do anything. Okay. And so we're going to define a function, and I'm going to tell you sort of right this second what it is, but this is something we're going to actually look into in a few days. Namely, it's a set of ordered pairs, and with a property. So we need to know, in order to understand what a function is, we need to understand what a set of ordered pairs is. To understand what a set of ordered pairs is, we need to understand what a set is and what an ordered pair is. So in the next few days here, I'm going to be going through some of this stuff, which you may find tedious for a while until you find out that you have to use it because you won't understand it without. I know what I'm talking about here. Okay. So I want to do some trigonometry, and I got to find it here. I'm going to put it up on a screen. And we'll talk about that a little bit, unless you don't want to. If you think you know all about this. Okay. Is anybody, I don't know if wants to comment, but do you see the trig thing up on the screen now?
Yep.
Okay. Now, the first page or so, okay, is trying to explain, first of all, and you, I hope you read it. If you haven't read it, I hope you read it soon or read it right now or whatever. But basically, we're going to be talking about things in the Euclidean plane. That's what you've been used to both in geometry and algebra. And one of the first things we do is talk about distance between 2 points in the plane. And this is called a Euclidean distance. There's actually other kinds of distances in math, but I don't want to complicate things. There are other ways to measure how far away we are from each other rather than this particular distance. For example, if you have two houses that are several blocks apart, I don't think you have, if somebody asks how far apart you live, it's usually how long it takes you to get from one place to the other, which might be on rectangles, because you don't cut through yards all the time, or maybe you do, but you don't drive through them. And so if you have a GPS, for example, and you first turn it on, and you want to find out how far is it to Kansas City, it may say it's 172 miles. 5 minutes later, you look again and it'll say it's 190 miles. And that's because at first it's giving you the airplane distance, and then it's going to give you the road distance. And I'm not sure that always happens with every GPS, but the point is it computes distances different ways depending on the vehicle that you're in. And if you're in a boat, it might be a straight line distance. But if you're in a car, it's almost never a straight line distance because you're on a road. In a boat, you're allowed to move around and get off a trail sometimes. So anyway, distance. Now you guys all know distance. And why do we need distances? Because we need circles. And a circle is, now, I'm going to say here, you'll notice here, I say the set of all points. Well, tomorrow or so, we're going to talk about sets. Well, yes, go ahead.
I just wanted to ask, where do we get that distance formula? Is it from the Pythagorean theorem, or where is it from?
That's complicated. Basically, what you do in math is you describe a set of things, like a set of ordered pairs, all right? And you make some thing like this. You say, okay, if I have two ordered pairs, I'm going to create this number. Now, it doesn't mean distance, it doesn't mean anything. It just means you're creating a number. And is it useful? Is it anything? In other words, what we could do with the ordered pairs, we could multiply the first ones together and multiply the second ones together and make a new ordered pair. Or we could multiply all four of them together, or we could add all four of them together. The question is, what do we get out of that when we do that? Okay. Now, because of the geometry for 2,000 years and the Pythagorean theorem, the Greeks knew about, for them, a number was a length. And so they prescribed everything as lengths. The trouble was they had a lot of holes in their system because they only believed in fractions. And let me tell you something about, and we can later get into infinities if you guys like. There are different kinds of infinity, okay? And if you had a line and you could throw a dart and hit one real number on the line, what is the probability it would be a rational number? And the answer is something I'm not even sure I like or believe in. The probability of ever being able to hit a rational number if you threw a dart and only hit one number is 0. There are so many more irrational numbers than there are rational numbers that you'll never be able to hit one. Now, that's saying a lot of stuff that I haven't tried to define, okay? And I don't know if that interests you or not, but there's two different kinds of infinity involved with the real numbers. And the Greeks only knew about the rational numbers. And that's it turns out that the rational numbers, the number of rational numbers is the same number as the number of whole numbers. It's the same infinity. But the real numbers, it turns out, is a different infinity. Now, I've got off the track here because of Mary's question. But basically, the Greeks measured stuff. They thought every length was a fraction and every fraction had a length. And when they came up with the Pythagorean theorem, the Pythagoreans realized that wasn't true because you could come up with something they proved was not a fraction, namely the square root of 2. Anyway, but because of the right angles that you can make in the plane, the distance formula, as you asked, does come from making a triangle out of the pairs. When you have a pair AB and a pair CD, and if I had a blackboard right now, I could say this quickly. The point is, there's a third point that you make to make a right triangle out of the 2 points. And once you've made that right triangle, then it's a Pythagorean theorem that you use to get the distance. Okay. Now, since you asked me that question, let me go off on a tangent here. You know, we'll be on the first section 1.1 all semester now. Namely, suppose that I said the distance was the horizontal distance, the distance between the 2 points was the horizontal distance plus the vertical distance, instead of what you usually call the distance. So what's the distance between 0, 0 and 1, 1 with that definition? And the answer is 2. So what in the way we're talking about distance, you're going to get circles when you say everything that's equidistant from a point. What do you get if you measure distance like horizontal plus vertical? If everything's one distance apart, what does it look like geometrically? In other words, what's 1 unit away from 0? Well, 1, 0 would be 1 unit away. 0, 1 would be 1 unit away. But so would 1/2, 1/2. 1/2, 1/2 would be 1 unit away, because 1/2 plus 1/2 is 1. So everything that's one distance away with this new way of measuring distance gives me a diamond shape instead of a circular shape, for example. And it turns out in math that's very important, but not for us right now. But there's all kinds of ways you can measure distance between things. The way we're doing it here is called Euclidean distance because it comes from Euclid, it comes from the geometry. So I appreciate the question. I just sometimes talk too much and then we won't be doing anything else in the day. But the distance formula does come from geometry, and that's why it's called Euclidean distance. If you guys know a little bit more math, it's a little L2 norm, but who knows, who cares about that right now? Anyway, so why am I want to talk about circles? Because trigonometry is based on circles. It also involves triangles, but it's based on circles. Now, I like to talk about this a little bit because what you're used to with functions, and remember we've talked about 1.1 a little bit, you guys have read about it, and the authors define functions 4 ways. He says, he actually described functions 4 ways, as I said earlier. Most things you've ever had for functions have formulas, and most of it's algebra. And so when I say f of x equals x squared, I assume you know what I'm talking about. And I assume you know what you do. If I said, if f of x is x squared, what's f of 2? I hope you say, well, f of 2 would be 2 times 2, that's 4. And what's f of 3, that's 9. And what's f of -1, it's 1, and so on. And what you're doing is filling in the formula because it doesn't tell you what the function is, it tells you what the function does. The formula tells you how to relate the pair. Now, the function itself, which we will get to in a couple of days, is that function I described, the squaring function, is the bunch of ordered pairs like 1, 1, 2, 4, 3, 9, -1, 1. It's a bunch of pairs. Now, what we do is we separate the thought of the pairs from the geometry. In other words, I can think about 3, 9 without thinking about a point in the plane. And the function, when you think of it as pairs, not as points, that's what's the function. When you think of it as points, that's the graph of the function. But actually in math, the graph of a function and the function are the same thing. They're both sets of ordered pairs. It's how we think about it. Are we thinking about it geometrically, or are we thinking about it analytically? Now, since I got off on this square thing, the trouble is with squares, and maybe, I don't know, here, I think I'm going to stop this right there so you can see me maybe. I don't know if that's good or bad, but you guys can vote and say, get back those notes and don't see you. That's okay. But one of the things about all of this is that most functions that you and I know about, or that we know about, do not have names. When you say f of x equals x squared, you're describing the function, but the function itself doesn't have a name. Now, if you say, well, it's the squaring function, okay, but have you ever seen that written down? Have you ever seen SQR of x equals x squared? I don't think so. Now, when people first built calculators, and I was involved in a little bit of this, when people first built calculators, on the little labels that you put on the plastic, they first had SQR for square. In your calculator, what is a squaring? If you want to square something, what does it look like on the little plastic piece? And I think it usually gives you like an x squared, something like that. Okay, but they first had SQR. And then they found out that that's bad because that could be square root. You see, and if you put SQ or SQR, which one is it? So in the end, they decided to put a picture on that tells you what to do, not what it is. Okay? That make any sense to anybody? Now, so you will learn, or maybe you know about the exponential function, but people usually don't write exp for exponential, although I do, and we're going to. People write e to the x. But that's not the function, that's the value of the function. So when we get around to doing functions in a couple of days, I'm going to be a little more specific and a little more careful, because this is where a lot of you make big mistakes on tests and homework. And I don't mean because I'm telling you, I'm talking about what you did in your past work. Okay. Okay, so because a lot of functions don't have names, we use a description of them rather than what they actually are. On the other hand, trigonometry, there are 6 functions and they all have names. Now, the names are not what you write. The sine function is SINE in English, okay? But what we usually write is SIN parenthesis X and close parenthesis, because again, you're used to describing the thing, not naming the thing. but the actual name for the sine function is the sine function, not sine x. Sine x is a nasal spray. You have to think that out. If you ever go to a pharmacy, you'll find that out. Anyway, I've had somebody, I asked students about trigonometry, and please don't do this on your next test. When I asked somebody what sine x is, they told me it's a nasal spray and they expected to get the answer right. So there's lots of things that students do. Like when people sign on, and when I think about that, let me take a snapshot of you guys, because I think everybody is here who is coming today. There's one person missing. Anybody know that left? Anything? I have one person missing. Maybe they decided to drop the class. Who knows? I hope not. So I'm going to grab you guys here. Just a minute. I've got to turn on the participants page. Sorry for this time, but I think it's the only way we can do it that makes sense and do it relatively quickly. Okay. Just a second. I gotta get it started again. Window. Okay. I think we took your picture. All right. Good enough. Okay. So what do I want to do with the trig? I'm going to go back to the share screen. You guys are awfully quiet. You ought to be making noise or something. I'm going to go back to the share screen and put the trig back up, because now we're ready to talk about that some. Where's the trigger? There it is. Okay. So what we have, and is a discussion a little bit about angles. Now, unless you guys want me to, I'm presuming you know the difference between a degree and a radian. Now, originally the Greeks just had degrees. Again, that's because they didn't understand real numbers. But another way of measuring things besides degrees has to do with what's called arc length. And unfortunately, the Greeks didn't have arc length because they didn't have calculus. And they didn't have real numbers. So they had trouble with arcs. So the first measuring had to do with triangles. Anyway, the whole concept here is, how do we talk about measuring something along an arc if we can't really talk about arcs? And so this is where they came up with angles and a circle. So if you would take 2 points on a circle and mark them off and draw straight lines to the center, you make an angle. And they measured the length of the arc by the amount of degrees in the angle, and they divided the circle up into 360 degrees. Nobody knows for sure why, but we think the Babylonians were trying to make the difference in one day, because you can think of the world we live in as a circular sort of thing. And I'm not trying to say something I know for sure here at all, but the point is that in every day, the sun changes like a degree. That's not exactly right, but that's what they sort of thought. And so it's sort of thought that they believed in a 360-day year, and that's of course not quite accurate, as we know, but we think that's where the degrees come from, but nobody's sure. Anyway, what's a better way or a different way to measure the length of an arc? And an easy way to think about it is the following. Suppose you're out on I-35. That's a road on the east side of Wichita that goes from Oklahoma City to Kansas City. I presume you know that number. Suppose you have a breakdown on your road and you need to phone in where you are for somebody to come and help you. What do you tell them where you are?
The mile marker or the exit?
Yes. And the mile marker is the length of the arc of the road. It's the distance of the road from the state line most of the time these days. And it's not an angle thing, it's a distance thing measured along an arc. Okay? And so it's a reliable way to tell about where you are. So if we put that idea, if our road was a circle like a racetrack, we could tell, like you talk about Indy 500, let's say that's an oval, not a circle, but basically you go round and round and round. And what did they do? They have a 500-mile race. They measure the distance you go around and round. And if somebody, you don't have to do this because you can see somebody that has an accident or something on a racetrack, but the point is they could find out where they are by where they were on the track by measuring the distance around. And they have a first turn and a second turn and a third turn. I'm sure you guys know all about that. And the point is that's how you locate people, is you go along the thing, not the angle from the center, okay? So arc length turns out to be something that the Greeks wanted to do, but they didn't have a good way to do it. We do now because we have calculus. So it turns out that angles can be measured two ways. They can be measured more than that as well, but two ways. And arc length allows us to do radian measure, and that's based on the circumference of a circle of radius 1, and that's where pi comes from and all that. Because again, the Greeks didn't understand that either, but they had a sense of it. But they didn't have real numbers, so they called it pi. They don't know what the length of it was, but they said they knew about what it was. But they named it something, and it's called pi. And so the distance around a circle is 2 pi, and we use that to base arc length on. Okay, so again, I'm talking about this. You guys can read about this. There's a way to translate from arc length to degrees, which I assume you know. It has to do with either pi over 180 or 180 over pi, if you can see what I'm circling now. And you can convert. Now, most of our time, we need to know about both. And so this paragraph here on page 2 basically says there's certain angles that you ought to know both degree measure and radian measure. If I say 90 degrees, you're supposed to know it's pi over something. Maybe I forgot.
2.
Anyway, you're supposed to know what it is if I say that, okay? It's pi over 2, okay? I didn't really forget. 330 you might have to think about a little bit, but again, you need to get used to certain degrees. And 30, 45, and 60, and multiples of those, and negatives of those are the ones that you need to know about, okay? So that's what that little paragraph's about. Now, we measure an arc from the horizontal, from 1O, and so forth. So you can read about that. So I want to talk about what the sine and the cosine function are, because you can't describe them by a formula. And when I say that, of course you can, but not initially. So what do we mean about a sine or a cosine? And what you'll notice here is I purposely did not make a picture because I want you to think about it. You can certainly draw a triangle or a circle and talk about this, but I want you to think about a circle. So this says locate a point on the unit circle. So do this in your mind, or you can write it down on a piece of paper where you are, whatever. The set of ordered pairs that you make is called the sine function if you take the real number. That's going to be a amount of arc length, but it's a number, and the height of the second coordinate, okay? In other words, if I have a pair of numbers on the circle and it's a unit circle, the second number is called the sine of the angle. So sines and cosines are defined by the ordered pairs on a circle of radius 1 with center at the origin. And what we do, and I think what I will do here real quick, let me go to something else here a second, and I hope I can do this quickly. Just a moment. There. Okay. Now, what I want to do here, just one moment, is roughly draw a circle. Okay. And I don't know how well you can see that. And you have a center. And what we do is we take a point on the circle, could be any place, and we make a vertical and a horizontal, we make a triangle. Now, can you see that, or is it too bright?
I can't see it. The circle, for me anyway, is out of the frame. I can see your right hand.
Ah, okay. So is that okay? Better? Anyway,
I can't really see it. I don't know if anybody else can see it. I can't really see it.
I
on
can
my
see
screen,
it.
I can see it.
It's good on my screen. It's just kind of, I mean, it's not really phasing in and out of flame or anything. I
All right.
mean,
Well, anyway, draw a circle. If you can see what I'm trying to do, draw a horizontal line on a circle. That horizontal line is 1, 0. And you draw a triangle. You make a point on the circle, whatever it is, point on the circle. If you guys can, boy, I don't know how to fix that yet. It's too bright. So let me see if I can dim it down a little bit. Is this getting better at all?
Yeah, it's better. I can see it now.
Okay. I'll just have to get used to that in the house here. The sky has not been as bright as it is today. So here's a circle. And the point I said you should take, if you can see my pen and stuff, I'm pointing at the point I picked. And I made a triangle. The height is an angle here. And so I'm going to make a bigger thing here. If I enlarge this, the angle is, we call theta, and that's the measure of the arc. Okay, that's how long the arc is. That's what the number means. Now, so you start at 1, 0 and you go up and you stop at some point. Now, the vertical height, that's the sine of the angle. And the horizontal is the cosine of the angle. And that's how the trigonometric functions are defined. Okay, now we first start with angles that are less than 180 degrees, but we actually can go all the way around the circle. And thinking of the sines and cosines this way, I don't know what you did in trigonometry in high school, but thinking of sines and cosines this way tells you a lot of things real fast. Like, for example, how high can that triangle be if I have a circle of radius 1?
1.
1. And so the sine function can never be more than 1. And it can only be 1 when the angle is 90 degrees. And right away, by doing so, just thinking about the circle a little bit, you get a whole bunch of trigonometric stuff that comes out of it. The cosine of 90 degrees is 0. Why? What's the x coordinate for an angle of 90 degrees from the center of the circle? It's the point 0,1. And the point 0,1, the O part, the 0 part, that's the cosine. So the cosine of 90 degrees is 0. People screw this up. People get it backwards. But the sine of 0 is 0, and the cosine of 0 is 1 because it's the length of this. When you are right here at this point, this length is 1. The cosine can never be bigger than 1, and it cannot be less than -1. Now, why -1? Well, if I have an angle of 180 degrees, what is this point out here? That's the end point of that angle. It's at -1, 0. Therefore, the cosine of 180 degrees is -1 because that's the x value along the axis that measures the arc. Okay? So that's the key to understanding the notes at the beginning. And then one more thing now, because we do have a right triangle all the time, we also can talk about relationships because this number right now is 1. And so what's the fraction with this height over this thing? What's we call it the opposite of the angle, the side that's opposite the angle over the hypotenuse. Make a fraction. It's the sine. When the angle is 1, when the length is 1, the sine is the vertical over the horizontal, but that's just over 1. And so the sine of the angle is the opposite over the hypotenuse in this case. What you learn about in trigonometry is you learn about similarity. You learn about other triangles. And now, if I don't have 1 here, if I have a bigger number, then the height no longer represents the sine, because remember, the sine can never be bigger than 1. But it turns out that triangles that are similar have common ratios. So if I call this distance A and this distance here B, if you can see roughly what I'm trying to write, it turns out that the sine of theta is also A over B. It's the opposite over the hypotenuse. So we define define sine function in terms of a circle, but we also have the sine function can be defined in terms of right triangles. And I don't know what did you guys do in trigonometry in high school? How did they define it? Circular or triangles?
I did triangles.
I'm pretty sure we kind of did a little bit of both. I mean, this is kind of both seems familiar to me, but same time different. It's hard to tell.
Well, the trouble is that the triangle way is the simpler way, and that's what they give to people when they're 14 or 15 years old, you see, because you haven't yet had enough algebra to understand functions. And so triangles is an easy way to introduce it. But the mathematical way is to do it with circles. Now, not that the triangles aren't mathematical, but I'm saying the preferred mathematical way is to do it with circles, because that's where we can prove things. And in mathematics, we prove everything. And the reason we do is because we didn't used to, and we were wrong most of the time. Okay, so
I'm just trying to get this right. So basically, to find the arc length, you just take the degree, and depending on what kind of angle is used, sine or cos, to find the arc length, right?
Yeah, you can convert it. Okay, but when we deal with derivatives and limits and integrals and all the things we're going to do in calculus, we always use radian measure. So we talk about angles in degrees because that's probably how you first learned about it. But when we do a lot of math with these concepts, we always use radian measure. So you got to learn how to convert. And so when we're doing mathematical things, we probably are always talking radians, even if we don't say 2 pi or pi over 7 or something. We just usually say, you know, x or something, and you know it has some length, but you don't worry about it. So yes, but what you said is correct. And as I say, we only translate these things back and forth when there's a reason to do so. So I'll talk about 30 degrees sometimes. That's pi over 6. I also might say pi over 6, and I hope you know that means 30 degrees. Whichever one you're most comfortable with is the way you ought to think about it. But what I'm going to try to do is to orient you toward radian measure because it's much more useful. The Greeks couldn't do it because they didn't have arc length. Okay, so for example, the Babylonians, the Greeks, were able to put 6 equilateral triangles in a circle. That's how they measured circle. They had arc, and not arc measure. They had chord measure, and they did a lot of things with pyramids and stuff with chord measure, not with arc measure. And a chord is 2 points on a circle that join. It's the length of a line that has 2 points on the circle, like a diameter is a chord. And they used chord measure, and they found out they could fit 6 equilateral triangles in a circle, which is why you talk about 60 degrees in equilateral triangles and things. Okay, and there's all kinds of stuff that comes out of what they had to do because they didn't have the right material to use to define. They wanted to do things with circles, but they couldn't really do it very well. They did wonderful things, by the way, with what they could do, but they didn't get as far as we've gotten now by any means because they didn't have the right number system. Anyway, I'm gonna get off of all that. I'm gonna go back here if I can find my thing here somewhere. Stop that share and go back to the other. Okay, where is this thing? Trig review. Okay, so what I do, once I define sine and cosine, in these little notes here, I only define two functions. There's actually 6 of them. Now, so I can quickly tell you, as you probably already know, the tangent function is the fraction made up between the sine and the cosine. It's the sine over the cosine. The secant function is the reciprocal of the cosine. And so the other 4 depend on the first 2. So you develop properties of the other 4 from properties of the first 2. And what I'm going to talk about, like, or in the notes here, is all the properties, not all the properties, but a lot of the properties we get by dealing with how we've defined the sine and cosine. And so and I don't want to go all the way through it here because it's 17 after, I don't have time anyway, but here I talk about the triangles that we just talked about. We have what are called cofunctions because the cosine is 2 extra letters and it's called a cofunction. So really the sine function is the only one that has its own name in a way. And then you have a cosine, we have a tangent and a cotangent. And you know, we have a secant and a cosecant, and we abbreviate these things. Now, what's an odd function? Something that's kind of strange? Well, the name of odd has to do with when you put a minus in something, the sign of a negative thing turns out to be minus the sign of the positive thing. Or the thing could be negative. I'd made it positive here. But it's when you are able to determine the difference between the sign of minus theta and the sign of theta. And it turns out it has a minus on it. So odd has to do with introducing a minus, but the cosine of going around the circle in the clockwise direction, 30 degrees, turns out to be the same cosine as going around the positive angle, 30 degrees, because the cosine is the x distance. And if you think of an angle of plus 30 degrees or minus 30 degrees, it's the same x value on the triangle. But for the sine, one triangle is up above and the other one's below. And so the sine of negative 30 degrees is minus the sine of positive 30 degrees. And we call one odd and one even. There's all kinds of reasons for that besides what I just said, but not today. So anyway, you go through all these rules. We have a law of cosines. Law of cosines is very important. The law of cosines is a generalization of the Pythagorean theorem. Okay? When I have a right angle, the cosine is 0. And then you have the Pythagorean theorem. So the law of cosines is a generalization of that when you have a triangle that's not a right triangle. And from this, you get a very important formula, the cosine of the difference of 2 angles. And from this thing, and you got to learn this one. You got to learn this one cold. You got to never make a mistake about it. And it's difficult in one sense, and to have a minus here and a plus over here. And when we get the hyperbolic cosines later, it changes. A minus goes with a minus, but I don't want to spoil your fun. For cosine, you have a minus here and a plus here. But later, for the sine, when we get around to the sine of the sum of 2 angles turns out to be the sum. You've got to get that right. But with cosine, it's cosine, cosine, sine, sine. With sine, it's sine, cosine, cosine, sine. That's a little bit, if you've never learned those, you've got to commit them to memory, not on your calculator, not in your computer, but in your head. We've got to use those at will, quickly. Then there's a law of sines and so on. Anyway, I want you guys to read this section if you haven't. Read the appendix if you hadn't. It's 20 after. Read the appendix if you haven't. Now, the appendix has some exercises, and there's also diagnostic tests on trig. We need to be good at that. We need to know how to do all those things. So what I want you guys to do is to go to the appendix and see what problems you can work and what you can't work. We would need to be able to work every problem in that appendix. That doesn't mean you work every problem in the appendix. I said you need to know how to work every problem in the appendix. So what I want you to do is go to the appendix. It's Appendix D, I think it's A24 in the appendix, and look at the exercises. Those exercises we need to know how to do because they come up in calculus every once in a while. And when they come up, we don't want to take hours to figure it out. We want to know how to do it. So please look at the review. When we get, sometimes the first test, which was the question was earlier about logic and stuff, sometimes the first test has some logic on it, it has some trig on it, and those are the two things people do worse on. So please study the trig. Now, anybody got any questions or comments or thoughts or anything, because we're over time, and how are you doing? Anybody? Well, I think we got to cut it off. I'm going to pause the recording.